Hello everybody, and thank you for joining me once again. We're looking at question number 5 on the 2013 Manitoba Math Contest. So hopefully you've given this one a try for yourself. I'll be taking a look at it right now. So 5 has two parts to it. Part A, given that AB is equal to 10, BC is equal to 12, and AD is equal to 5, evaluate A plus C times B plus D. Now, the expressions that they give me here are all products, and we've got a sum here. So how can we turn these sums, which admittedly are multiplied together, into expressions involving these products? Well, let's just expand it out. A plus C times B plus D. That's going to be AB plus AD. Well, A gets multiplied to both of those, and then C gets multiplied to both of them as well. CB plus CD, which most people stylize alphabetically. So I'll change it to BC and CD. Okay, what are we to do now? Well, we've got a whole bunch of pairs of products. And what did they give me? Pairs of products. Here's AB, here's BC, here's AD. These are some of the ones we already have. 10. I think this was 5. CD was the other one, right? No, AD was the other one, and 12 was BC. Okay, we just need CD. But they didn't give me CD. I'm CD-less. What can I do? Well, perhaps, since all these things are multiplied together, I can find a nice, clever way to multiply them all together, or, divide some by some other ones and get CD all by itself. So I have AB, I have AD, and I have BC. Well, these two give me the components of C and D, but with an extra A and a B. So AD times BC, but I want to get rid of this A and this B. Well, fortunately, I've got AB right here. Okay, so CD is just going to be 5 times 12 all over 10, so that's 60 over 10, or 6. So my sum is 10 plus 5 plus 12 plus 6, 15 plus 18, a final answer of 33 for A plus C times B plus D. All right, so that's 5A done. 5B now. A rectangle is cut into 4 smaller rectangles by 2 perpendicular lines. Okay. 4 of the 5 numbers 6, 9, 10, 12, and 15 are the areas of the 4 smaller rectangles. Which one is not, and why not? Okay, so we got to justify what we're talking about. Let's draw a quick little picture. So we have a rectangle here, and it's cut by perpendicular lines. They say we get 4 rectangles. Okay, now we've got the numbers 6, 9, 10, 12, and 15 here. Okay, well, I don't know which ones, obviously I don't know which ones should be assigned to which, because I have no idea what the area of the original thing was, or what parts these things were cut into. But inspired by 5A, I'm going to give some names here. I'm going to call this A, and this C. I'm going to call this B, and this D. Okay. So then the overall area, A plus C times B plus D, is really just the sum of the 4 rectangles. Okay. So that's AB plus BC plus AD plus CD. So I sort of have to assign these to, maybe 6 is B times C, but how can I really tell? How can I figure all that out? Well, if I take this pair and I take this pair, they multiply to the same thing. AB times CD is really just, ABCD is really BC times AD. So maybe there's only 4 of these that multiply to the same thing. Better yet, so I'm trying to avoid guess and check. That's the idea behind what I'm doing. And so while it's true that some pair here must multiply to the same product as another pair, and then that would actually solve the problem completely. How I get that pair right now, I just have to say, well, maybe 6 isn't the one that works. Check, does that all work out fine? Maybe 10 isn't the one that works. Check, does that all work out fine? I want to avoid guess and check. Okay. Now, depending on who you are and how fast you can do mental arithmetic, at this point, just saying, okay, let's take 6 out, does it work? Let's take 10 out, does it work? Let's take 12 out, does that work? That might work fine for you. Okay, and we're still at the first half of the contest, so speed is pretty important, but I want to be a bit more exact just in case next year they have the same question, but suddenly the rectangle's been split into 9 and I have to pick the odd one out, and that's going to require a bit more effort. Or next year it'll be split into 2,000 and whatever, and that happens to be a perfect square or something. I don't know. So what can I do? Well, AB times BC times CD times AD is really just A, B, C, D all squared. Now this is the product of all of them. And so what can we do? Well, I'll take a look at 6 times 9 times 10 times 12 times 15. So this is going to be a perfect square multiplied by some extra number. So 6 times 9, it's probably easier to write them as 2 times 3, 3 squared, 2 times 5, 2 squared times 3, and then 3 times 5. So note immediately that if 10 is in, so is 15. In fact, I don't even need to look at this. I just need to get products to be a perfect square. So if 10 is left out, then there's no 5 to pair up with the 5 and 15, so we wouldn't get a perfect square. So 10 can't be left out, as 15 would bring a 5 that wouldn't have a pair. So it wouldn't have a match to make 5 squared in our perfect square. So that tells me 10 is in. 10 can't be left out because that would mean 15's in, and 15 gives me a factor of 5 that I would need. So 10 is in, and similarly, so is 15. Now these guys bring a 2 and a 3 to the table. Okay, what can I do? Well, with this 2, I need to get some other 2's, and I only have 2 other places to get 2's from. But the 2 squared would still leave me with an extra 2. So 10 brings a factor of 2. The reason I didn't end up multiplying this all out, though, by the way, is because I think it would be kind of a big number. Although I suppose I could, what is this? This is going to be 2 to the 4, 3 to the 5, 5 to the 2. So that tells me that we got an extra factor of 3 kicking around here. So yeah, actually let's do that argument. I didn't think it would work out, but so this equals the odd number out times a perfect square. By looking at the exponents, this is a much cleaner argument. There is an extra 3. Okay, there's a 3 around that we cannot allow. So, 6 or 12 can't be allowed. You know, you remove 10, you still have the extra 3. Oh no, I guess 15. 15. So 6, 12, or 15 can't be allowed. Therefore, 9 and 10 are in. But 15 is needed to pair 5s with 10. Therefore, 6 or 12 can't be allowed. Okay. But ten also has an extra factor of 2. So we need an odd number of 2s to square everything up. So 6 is needed, not 12. So 12 is the odd one out, and I have thoroughly explained why by looking at prime factorizations. A lot of writing for that one, but I would say it was straightforward once I realized I needed to multiply everything out. And I would have gotten the same, so I was sort of doing the same reasoning the first time anyway. I mean, I showed why 10 and 15 have to be in, but that was far more verbal, I think, having these prime factorizations here and then ultimately multiplying them out. I don't know what this number is, by the way, and it doesn't really matter, but it's the odd number out times a perfect square. You know, this guy up here, he's k squared. Okay. So, realizing that the 9 and the 10 are in, the 9 doesn't really do anything, but the 10 brings both the 15 and the 6 in, and that leaves 12 out. Not a bad question. I like it. It's kind of interesting. And as I say, I think it could be nicely generalized. So imagine another question where we've got, a big rectangle, but a whole bunch of other lines all perpendicular divided into, say, 6 rectangles or 60 rectangles. Choose out of this list which one can't be allowed. I think there's some merit to there to making the question a little harder. That's some of the things that I think about in my spare time. Anyway, join me in the next video for question number 6 on the Manitoba Math Contest, and I will see you guys there.